everyone. Good afternoon and welcome to this webinar on FRED. Before we get into the main topic, just like to talk briefly about us. CBS are the main distributor for photon engineering's FRED optical software. We actually sell and also support FRED across most of Europe, and we have staff in 3 countries. As for myself, is Neil Barrett. I have a master's in optics, and I've actually been working in optical simulation for around 17 years now. For those of you that are joining us that are also new possibly to FRED, just first of all, some points on what FRED is. FRED is a comprehensive optomechanical systems design software tool. So we actually trace rays to analyze lots of different optical systems. We can calculate stray light. We can also deal with coherent beams, analyze imaging systems, also illumination ones, and that one's bolded because we're going to see that in a demonstration that follows. We can also deal with lots of other topics in here. So we can deal with thermal self-emission, tolerancing. FRED can ray trace in lots of different modes. And FRED also has a multivariable optimization capability, which is also, of course, one of the main topics of today. And another special trick that FRED's had is it can ray trace using GPUs, which is incredibly fast. So today's topic is optimization. So first of all, what is that? We're going to talk about optimization very generally first, and then we'll take a look at a sample file where we'll see FRED optimize. So optimization algorithms in optics, they perform a very special process. They allow us to take an optical system and apply changes to that optical system with the intention of making that system better than our starting point. And to optimize, we need a couple of things. We first of all need variables, and that is a table of things that the software is free to automatically change. So they include things like curvatures, locations of optics, tilts, anything like that. We also require targets. These are a table of calculations of things that we wish to measure to actually decide whether or not our system is getting better or getting worse. And they include things like spot sizes, the power that we measure on a given plane, various things like this. So taken together, that table of variables and also targets set out the merit function space within which optimization takes place. So the merit function is a key component of how we optimize. The merit function is essentially looks something like this. And it's just to explain what's going on here. This variable vector x, this vector x here will contain all of the items which we can vary. So that could be a curvature, a z location of an optic, things like this. And we have m variables. So these all describe things that we are free to change. And when we've chosen values for these, which is something that the actual optimization function does, that defines some position x in variable space. And in the merit function, essentially what we do is we look at each position we're at, we calculate the value of the thing we're interested in. That could be the value of the spot size, the value of the power, whatever. And once we know that value, we subtract from it the target that we want, when that difference is squared so that the value is always positive. And this value minus target essentially describes how far we are from where we wish to be. This value is multiplied by a weighting factor, and this is combined in a way that we call this the actual aberration itself. The merit function is then simply the sum of all of these differences, how far away we are from where we wish to be. So the merit function is the sole thing that represents what is better in our optical system. The the lower the value of the merit function, the better our system is. And an ideal merit function is 0. And that only happens when every single value matches every single target that we want. So if we think about a very simple system before we look at something more complex, if we take a very simple sample file like a simple lens, so this lens is completely fixed. The only thing that's free to change, the only variable that we have is the back focal length. So how far down in Z we actually choose to measure something. And the item that we're going to measure here is one thing, which is the spot size. So we only have one variable and one aberration. And in this case, our ideal spot size is 0, so our target is 0. So the merit function collapses to be something very, very simple, which is literally just the spot size as a function of Z. And if we plot what that spot size looks like as we move down Z, we get this nice parabolic graph. It's parabolic because it's value minus target squared. And this gives us some ideal point to place our plane for the minimum spot size. So that's a very simple one-dimensional case. At some points in my life, I've been asked, well, why do we need optimization at all? Okay, can't we just iterate through every single possible answer and pick the one that's best? And that as a methodology doesn't really work. If we take a slightly more complex system, perhaps something like a simple landscape lens, a landscape lens is just a single piece of glass and a stop and an image plane. If we assume, therefore, we have 6 items that we can vary, so we can change the front and back radius of curvature, the distance of the lens from our stop, the thickness of the lens itself, the distance from the lens to the image plane, and we can also choose the index of the glass. That gives us a variable vector x with 6 things that are changing. Now, if we assume that each one of these items can take on 100 different values, then 100 to the 6th power gives us 10 to the 12 permutations of that system, which is a huge number. Now, even if you assume that you can trace and measure 1,000 systems per second, which in a non-sequential trace with lots of rays bouncing around is pretty fast, you find that that sort of brute force approach would take 1 to the 9, so 1 billion seconds, or around 32 years. And clearly that's not a feasible way of doing things. So instead, we use optimization methods, and they're needed for virtually all non-trivial problems. And merit function algorithms are often split into 2 different camps. There's the local methods and the global methods, and they are intended to find local or global optimums. The local optimum is the best answer we can find within a given region of space, moving continuously downhill. The global optimum is the best answer possible with the lowest merit function. Now, the issue, of course, is that even if we found the global optimum, we would never be able to prove it. Because to do so, we would have to demonstrate that every other answer is worse. And the only way we can do that is to iterate through them all. And we've already seen that takes an inordinate amount of time. So merit functions and optimizations will always give you, or will hope to give you, a better answer, but there might be better answers out there still. So merit function space is pretty complex. If I try to draw it in a very simplistic way, this vector along the x here, this represents some points in our m dimensional variable space. As we go along, we'll find these minima where things get better and then they get worse again, and the merit function gets better and then worse. Each bottoming out zone, each little valley here represents a local optimum. And the best value of all of these is the global optimum. Okay, so these are the things we're trying to find, and hopefully we're trying to find better answers. Now, there are multiple optimization methods out there, and the one that FRED uses is called downhill simplex, which is also known as the Nelder-Mead method. And a simplex is a geometric construct with m+1 vertices, where m is the number of variables that we have. So if we think of a 2-dimensional problem, then the actual simplex shape itself is a triangle. And this little illustration here shows optimization taking place in a 2D variable space. And we can see how the simplex is a triangle shape. And generally speaking, this triangle walks around and walks downhill to this local minima, which happens to be in the bottom of this valley here. So the way that this method works is that all the points on the simplex are actually calculated. So there are 3 points in this case. The worst value is discarded, and then the algorithm chooses a new point and the process restarts. And in this way, the simplex walks its way downhill to a better solution. The simplex method has some plus points and some negative points. The positive points for this method is that it is very robust. It doesn't use gradients at all. We only need to be able to actually evaluate what the merit function is for each point on our simplex. And that means that it works in the presence of very noisy or also highly non-linear merit functions with step changes in and things like this, which gradient methods can't handle. So the method is robust and works exceptionally well. The downsides to this method, though, is that the user has to specify a few more data points. So we have to specify upper and lower limits for every single variable that we have. That limits how big our simplex can actually be. We also need to provide a fractional step for each of those. That is essentially how far the software can move in terms of picking its starting simplex. And we also need to define a termination threshold, which is essentially a limit at which the algorithm stops, otherwise it will run forever. The other downside to the simplex method is it's not the most efficient method available in terms of optimization algorithms, and that's the price we pay for the fact that the algorithm is so robust. So this method might incur a few extra iterations, but generally speaking, it works exceptionally well. So that's hopefully enough background on the optimization kind of idea and what we're trying to do and the background to the method. We're now going to take a little look at a demo and see this happening within FRED. Here I have a fairly simple system. I have a plane over here which I'm using to collect light and measure total power. And the system that we wish to optimize is this hybrid lens. Okay, so this is a total internal reflection hybrid lens. So we have an LED source that's emitting light in all angles. Some of the light will transmit and actually refract through these optical surfaces. Other parts of the light will hit this optical surface at a high angle and totally internally reflect. And we want to maximize, or sorry, we want to optimize this shape to maximize the amount of light I get on my plane further downstream. So if I just run a ray trace first of all, and then calculate how much light is on my plane downstream, I have about 0.5 watts total integrated power. Okay, and that's the value that I have here. Okay. So to take a look at the file, what are we going to optimize? Well, this geometry is quite interesting in of itself. So the geometry, if I just take a look up here, you can see there's a couple of different curves. So these 5 segments of a curve are joined together to create a larger hybrid profile curve. And that curve is used as a surface of revolution to create this shape. Okay, so these are the things that we have. So the actual shape itself is a surface of revolution using this curve, and this curve is defined from multiple other curves. Okay, so these 5 curves build this larger object. If I just take a look at these curves first of all here, I can just set them all to be traceable and focusing on these curves. The first curve is this one down here. So this curve is the first segment that follows the profile of the light emitting diode. There's then a small flat, which is curve 2. Curve 3 is this larger sweeping curve that defines the edge. we're going to optimize the shape of this curve. Curve 4 is a flat piece that joins to the next curved surface. And so curve 5 is the final curved element here. And curve 5 we're going to optimize also. Now, these curves actually have multiple points. So there's a point in the midpoint somewhere around here. There's a point at the end somewhere around here. And what we actually want to do is we want to essentially vary where these points go in space. So these points are going to be free to move in Y and also in Z. Okay, there's a point to optimize down here. This one is free to move only in Z. This point here is free only to move in Y, and it's locked to this point in Z. And then there's another midpoint over here, which is also free to move in X and Y, sorry, in Y and also Z. Okay, so these are the points that we're going to vary. So these are all defined as variables. And let me just take these surfaces and make them not traceable again. So these surfaces are all defined, or these points are all defined as variables in the optimize section of FRED. So in the optimize area, we can go to define edit. And in this area, this is where we see the variables that we have, the merit functions that we have, and the method that we want to use. Okay, so just first of all, to talk about this table, variables table. So this defines the points of the curve. Okay, so there is along curve 3, there's a midpoint here. This midpoint is free to move in Y and Z. There's some limits on where it can move to. And essentially all of these points are limited within a 12.7 millimeter box is essentially how it's set up. There's also a weight option for each control point, which will choose how closely the line follows each point. So that is also made a variable at the midpoint. The end of the line is also variable in Y and Z, which are these two here with the two endpoints. And we should say that FRED has lots of different things that we can optimize on. We can actually variable, okay, we can make vary. So there's a whole table of things here. We're just concentrating on the NURB items because this is the shape that we're going to optimize in our case. The other items that we vary in here are curve 5. Curve 5 is this front part of the lens. So we're varying the Y height at this point. The Z point is actually locked to the Z point of the end of curve 3. Okay, and we do that via a pickup solve. So I just show you that's also in the optimize area. So in the pickup solves area, I'm choosing the Z component of the end of line 3 and choosing that the Z component of the start of line 5 is the same. Okay, so they're matched up in the Z planes. And we then have some more points that we optimize in here as well. So we're optimizing the Y and Z points of a couple of items down here. Okay, so it's constrained to a box, but the points are free to move around within it. There's then the merit function aberrations. These are the target values that we wish to actually have. So the merit function here is again fairly straightforward. We have a target for total power, so total maximized power on our analysis surface. So that maximizes the power that we have there. And there are also a couple of user scripted aberrations as well. And what these scripts are doing, the scripts are very short, they're not very complicated at all, but essentially what they're doing is taking a look at the midpoint on curve 3 and making sure that it doesn't go past the end point of curve 3. So we're making sure that these curves stay sensible and they don't go past each other in ways that we would rather not see. Okay, so just some fairly simple limits being applied within those. And then at the very end is also a post-update script. So the post-update script, when FRED has varied some of these points, we want to make sure that the end of surface 3 still matches up with the start of surface 5. And so there's a very simple script here which updates curve 4, that linking curve. So again, a very short script, just to essentially make our surface into one continuous object. So if I choose curve 3 here, and let's just change the Z coordinate from 11 to 12. If I apply that change, you'll see that the model updates, but all of the surfaces are still stitched together and there's no breakages in the surface. Okay, so we're achieving that with pickup solves and also post-update script. So that's everything in place that we need to optimize. The last section that we need to think about really is the optimization method, and we're going to use the downhill simplex method. Now, FRED does have some other options, and we don't have time to talk about all of them in a 30-minute webinar, okay? But this is where FRED has some global optimization options, such as simplex with multiple restarts and also simulated annealing. Okay, but we're just going to use this local simplex method here. And in this tab is also where we choose what the convergence criteria is. So when the variables change, becomes very small, when the merit function change becomes very small, or after some number of attempts, we can choose to stop optimizing. And the first one of these conditions that are tripped will stop optimizing, okay? So that's everything. Everything is set up to optimize. So to call the optimization itself, what we do is we just choose the optimize option from the optimize tab. And here we'll see now that the surfaces will start to change shape as FRED is moving those control points around in space and updating our curve. And each point is going to try to make sure that the total power becomes larger than it was previously, and that the surfaces maintain some realistic shapes. Okay, so as you can see, quite a lot of changes going on there. Now, while this optimizes, I'm just going to switch back to the presentation here and just talk about some general comments on optimizers. There is no such thing as a perfect optimizer. The algorithms perform in different ways. Performance is measured in terms of both the answer that they find and the number of iterations that they took to get there. And different algorithms perform differently from each other given the same problem and the same starting point. And we don't know in advance which algorithm is going to be best. If we did, of course, we'd always choose that algorithm. Or if we knew exactly what merit function space looked like, we wouldn't need an algorithm. We'd be able to just pick the best point. Now, one thing that is key about local methods in particular is that the answers found from the optimization are generally a pretty strong function of where we start. So that kind of initial simplex, when that simplex is made, you can run the optimization as many times as you like. That simplex will always walk in the same way to the same local minima. If you choose a different starting simplex, it will walk in a different way and find a different one. So what this tells us is that choosing a good start point is actually something of a skill within itself. And choosing good start points, we can use some intuition, we can use prior art in terms of Lense databases or illumination databases. We can start with the product that we designed last time around, the last year's model, and try and update that one. But essentially choosing a good design start point is something of a skill. Let's just go back to FRED here and see where things are. It's still optimizing. I think we set this to finish after 10 iterations. So this is the end. And this is the end point of our design. So this is still sensible because we bounded where the points on the curves could go. And if I do a ray trace here, let's just trace all sources again. So we started out with 0.5 watts of power on our plane of interest. And if I take a look now, at the plane of interest, we can see we have this value up here, right? So we have 1.8 watts of power, so nearly 4 times better in terms of total power. So the optimizers helped us out a lot there. So that hopefully is just a nice intro to how we can optimize in FRED, so the power that the software has and how we set problems up. If any of you have any interest in, or have any issues with doing this on your own FRED designs, then of course you can get in touch with us. There's further information and support on the website, on our blog posts. We have technical support available. Also have Photon engineering knowledge articles, have a lot of great content also. So I think that brings us up to the end of the 30 minutes here with a short space for some questions and answers if anybody has them. Inside of the Zoom meeting, there is an area where you can type questions. So if you have any questions, then feel free to ask them now, and I'll do my best to answer them. Is this example available, is a question from Johan. It's not generally available as a sample file because I actually made this ourselves in-house, but I'm happy to share it. So if anybody would like a copy of this file, then please just email us at the support address, and of course we'll be willing to share it. So yeah, Martin's also asked, asked the same question. Yeah, of course, bear in mind that you will need FRED Optimum in order to run the optimization features. Okay, the optimization features are only available in FRED Optimum, which is the middle version of FRED. If those of you have FRED Standard and you'd like to try Optimum for some time, then we can also arrange that. We just need to update your key for a couple of weeks or so that you can try this out. Any further questions from anyone? No questions coming in further, I think. So on that basis, guys, just like to say thank you for taking your time to join us. Future webinars will be announced. I'm not sure the dates of the next webinar, but there is a webinar coming up on coherent beam propagation in FRED. So that's the next one that we're going to do. So keep an eye out for that one. And we'll see you at the next webinar or the next training course or the next trade show. If you visit any trade shows, of course, please drop by our booth. We're always happy to have a chat and learn about what you guys are doing with FRED. Have a great afternoon, and thanks again for coming. Cheers, guys.